Okay, so today we were writing insertion sort, or a modified insertion sort, to practice turning a approach to something into a Python algorithm or Python code. So let's go ahead and write that. So if you remember from last time, the normal cadence for this guy is you have a list, you start off these two different values at the first bucket of the list. CurStart just keeps walking from beginning to end, and the follower bubbles a value up towards the beginning as much as it can. All right, so we're gonna come over here, and is this us? Yep, this is us. Okay. All right, so let's go ahead and let's write a couple of the pieces that we know we're going to need, and then we'll ask the questions along the line. We know that CurStart, this variable I defined right here, will go from 1 to 2 to 3 to 4 all the way to the end of the list. We know that is a fact. That's how many times we need to take that value and try to bubble it towards the beginning. Okay? So I'm going to go ahead and write for CurStart in range 1 to length list of numbers. So this will take CurStart on that voyage. Okay? So it'll start at 1, then it'll go to 2, then 3, then 4, all the way up to the length minus 1. All right. Now each time through, we want to reset the follower to be equal to the current value of CurStart. The follower is equal to CurStart. Now, one thing that I had several questions about, there's two different things I'm representing here. In the blue, these are the values. This is the value at bucket 0 in the list. This is the value at bucket 1 in the list. This is the value at bucket 2 in the list. I'm using CurStart and the follower to access these indexes. This is bucket 0, bucket 1, bucket 2, bucket 3. It's important for me to have access to the individual positions that I'm at in the list. And then if I need to get the value at that position, I can say list of numbers at bucket 1, which will get me the 3. List of numbers at bucket 3 will get me the 5, so on and so forth. The reason it's important to do that is if I instead had the follower point at one of these values. So the follower in this case, let's say, held the value 3. I have no way of finding out where in the list that guy lives. I can't get from 3 to 1. But if I'm pointing to the 1, I can get from 1 to the 3 by saying list of numbers at bucket 1. So in this case, I'm using the index 1 to get me the value that lives at that position, which is 3. All right, so by keeping track of these indexes, by keeping track of where I am in the list, I get the ability of knowing where I am as well as the ability of getting the value at that place. Whereas if I'm just keeping track of the value, I have no idea where I am. All right, so CurStart is going to be one of these indexes. It's going to start at 1, then go to 2, then go to 3, then go to 4. The follower will always start off at whatever CurStart currently is. Then we ask a question. Should the value, well, we ask a couple of questions. We ask, are we already at the beginning of the list? Once the follower is at bucket 0, we don't have a guy before him to compare him to. All right, so he needs to be greater than 0. So if the follower is greater than 0 and, okay, so assuming he's greater than 0, and the value of list of numbers at the follower minus 1, that is this guy, should come before this guy. the value at bucket 0 should come before the value of bucket 1. If that's the case, then we'll do the swap. So, and list of numbers at bucket the follower minus 1 is less than list of numbers at bucket the follower. If both of those conditions are true, if we're not at the beginning of the list and the guy before me is smaller than, I'm sorry, actually, the guy before me is greater than me, or I can say I am smaller than the guy before me. Those all mean the same thing. So should the current value come before the value before him? That's what that says. Not at the beginning of the list, and should I swap? If both of those conditions are true, we're going to do a swap. So we'll say temp is equal to list of numbers at bucket the follower, then list of numbers at bucket the follower is equal to list of numbers at bucket the follower minus 1, and then list of numbers at bucket the follower minus 1 is equal to temp. So preserve the value of position the follower, overwrite that position with the guy before him, then overwrite the guy before him with the original value of bucket the follower. And then what does the follower do? The follower follows. All right, so if we do a swap, the follower will then follow that guy. So that's minus 1. As soon as this if fails, that is, we either get to the beginning of the list or we shouldn't do a swap, we will exit this if statement and loop back up. Now, this if statement, this question we're asking, is something we don't want to just ask one time. We want to ask this over and over and over again. So instead of asking the question once in an if, we want to ask it in a while this is true. While we're not at the beginning of the list and we should do a swap, what do? We swap and decrement the follower. Do this over and over and over and over again until we finally fail one way or another. We'll either fail when we finally get to the beginning of the list and we have no guy before us, or when we get to a place where we decided I've bubbled this thing towards the front of the list as far as I can go. All right, so when this finally fails, we'll fall out of this while loop. We'll loop back up. We'll get the new value of cur start. That would be like cur start is now equal to 2. Then we'll reset the follower to equal cur start. And then do that same logic again, bubbling it towards the front. All right, so now that should be it for insertion sort. It scrolls so fast. So here's my list of numbers. I have 100 numbers randomly between 1 and 1,000. I go ahead and well, I'm currently not printing out those numbers, but I could print out those numbers. So this will show them not in order. And then I'll do like a little print, little divide section there so I can see where that ends. And I'll call insertion sort on that, and then I'll print out list of numbers. my original list of numbers. List of numbers, passes in here, insertion sort. Takes in list of numbers, goes through all the guys, swaps when we're supposed to. Make sure I'm not making a bad assumption here. Yeah, I'm not. Let me get rid of this extra code right now. I'll come back and mess with our player later. Why is this guy not sorted? Print out our list, call insertion sort passing of that list. Insertion sort takes the list. Start goes from 1 to the end of the list. Set the follower equal to current value of start, as long as the follower is greater than 0 and the value at bucket follower is less than the value at bucket follower minus 1. Then we'll do our swap. So temp is equal to the follower. Overwrite the follower with the follower minus 1. Oh, overwrite the follower minus 1. When I had deleted some of that, I messed up my code. So there's our sorted value. And notice that list of numbers is passed by address. So it came in as an address. We made changes to it here, and those changes did have side effects. So we saw those changes out here. We printed it out. All right, so here's unsorted and here's sorted. And this is the algorithm that we wrote in, well, that we described at the end of last class. All right, questions about that?
Is there a reason you don't return anything, or do you just not need to do that?
It does not need to return anything because this guy is passed by address. So when we made changes to him in here, those changes were happening in the actual place in memory. So that when we came back out here, we realized those changes. I wanted to show you a picture of that. And actually maybe for the sake of this example, let me call this guy LOL. Actually call it LON, so that it's almost a reasonable variable name. LON for list of numbers. Okay. So inside of insertion sort, we take in a parameter called LON, and I operate on LON inside of here. But the value that I passed in was my list of numbers. So if we draw a picture of that, this is my, uncheck this, there we go. So if this is my list of numbers in memory, I have inside of main something called list of numbers. This is our main scope. We listen to like band music. And inside of, so this is called LON, inside of insertion sort. So these are two different functions. We have the main function that has a local variable called list of numbers. We have our insertion sort that has a local variable called LON. Now we called insertion sort from within main. And I'll actually show that call in here as an example. And we passed it our list of numbers. So we already know that our list of numbers points to this place in memory, our actual list. Then when we called insertion sort, passing it list of numbers, remember insertion sort takes in a single parameter, we're passing it a list of numbers here, and it calls that parameter LON in my example here. So now what I have is a second variable that points to the exact same place in memory. It's not a copy of it. This is passed by address. This lists are passed by address in Python and in most languages. List type things are passed by address. So that means this guy only exists one time and we have two different ways of talking about him. If we're inside main, we can talk about him using the handle list of numbers. If we're inside of insertion sort, we can talk to him using the handle called LON, variable called LON. All right, so inside of insertion sort here, where I made all these changes to LON, those changes were being made in the original memory up here, so that when I got back to main and I printed out my list of numbers again, I was printing out that same modified list of numbers because both of those variables point to that same place. That's why we don't have to return a value, because we modified that value in memory. There's nothing to return. We made some changes and we said, okay, my artwork is done, and we left that portion of the code. That makes some sense?
Yes, thank you.
So that's a really important concept. So I'm glad you asked the question. I know we've talked about it several times, but it's super important that we understand that concept, because when we're passing something like a list to a function, any changes we make to that list will have side effects. We will realize those changes outside of that. But if we're passing something like a number, so let's say we have a number is equal to 5 here or something like that. Actually, I'll represent. All right, and then let's just say inside of insertion sort, I'm just making this up, we have a variable called num. And let's say a number was passed in as num. It gets passed in by value. So num and a number are pointing to separate places in memory, because a number held a numeric value. Numeric values are passed by value, not passed by address. So since they're passed by value, what insertion sort would have gotten is a copy of that value. So if he changed this guy to a 7, this guy did not change because he was a copy. So things that are passed by value do not have side effect. Any changes that we make here does not impact the original. But things that are passed by address, like lists, do have side effects. So any changes we make here impacts the original value. All right. So in a language like Python, let's just drive this point home. We say pass by value, call this no side effect. These are things like integers, chars, strings, floats. So in general, we would call these guys our, in fact, actually, these are our primitive types. Types that are built into the language. Strings are our outlier in that case. And just to kind of show you that real quick. Have this guy take in a string. So we'll say s is equal to hello, print s, change string s, print s, and we see that it's still hello. Whereas if I were to print it out inside here, proving that we did change a string, we see we have the world in between there. So in that example, I'll just draw our same thing as we did here. We now have, in fact, I'll get rid of, well, I'll actually reuse those variables here, but I'll get rid of our num and give ourselves a more specific example. I guess I could drag that quicker than that. So now I have another function called change string. And change string has a parameter called a string. And over here, inside of main, we called it s. Notice here in main, I have a variable called s. I said equal to hello. And inside of change string, it's called a string. So s is hello. And when we first pass it in to change string, it's equal to hello. But strings are kind of treated like a special case. Most of our modern programming languages treat strings like a special case because we pretty much use strings like they are primitive types. That is, they're values built into the language that we kind of toss around willy-nilly. They're just really common types. Generally, I would say a definition of a primitive type would be a built-in type that can only hold a value. But then we'll put in parentheses here, except strings. Because strings can do more than that. You know, they can, well, actually, in Python, strings can't. Python, we have functions that operate on strings. But this is still a mostly true statement, that strings are a little bit more complex animals than like an integer. But in most programming languages, strings are still considered primitive types, or at least they are They behave like primitive types, which I guess is the better example here. Whereas when I passed this string S to change string, a copy of it was created. So even though this string S is kind of like a list, right? We've seen strings, they operate like collections. It's a list of characters. Strings specifically play by the set of rules that primitives play by. That is, when I called change string from in here, and I passed this guy S, S was duplicated and passed to change string as a copy. So that when I change this guy to world inside of change string, that's what I did right here. I changed it to world, and then I printed it out, proving that it did change. It changed. It did not have an impact on the original value because I had made a copy of it. So that way, when I came back to main and I printed out the value of S, the value of S is still hello. So here's the original value of S. This is a string inside of change string after I changed it. And then here is evidence that that change was not permanent, that strings were passed by value, not passed by address, because S was still its original value when we came back out. So here's two examples that are very related to each other, since we think of strings as kind of as being collections or collections of chars, and we think of lists as being collections of stuff. I'm telling you that Python specifically treats strings as a special case. All other collections like dictionaries and any list are passed by address, which means that we make a change to it. That change happens in memory and will have permanent side effect because both our variable that was originally in existence and the local parameter where we passed it in, both are the same value in memory. All right, so important slide to wrap your mind around if you haven't quite gotten there yet. This is something that's important, transcends all of programming. All languages have this concept of pass by value and pass by address, and you can pretty much rely on all of our collection types except for strings in all languages to pass by address, and all other types, including strings, to be passed by value. Every now and then there'll be a little shift in that idea, but that's pretty much par for the course. Okay, so questions about that concept. All right, so let me give you this code now as, we'll call this our current solution to insertion sort. Actually, I can give you less of this code. If I just give you insertion sort. So I'm going to give you some more stuff. Okay. So now I'm going to get rid of change string here. I'm going to get rid of that stuff. I'm going to put some of the stuff we already had in there back in, but we'll just write that again real quick. All right, we want to go back to our idea before that we were talking about players. So our ultimate goal here is we want to create a bunch of players, and then we want to sort those players using insertion sort on their age. All right, so just foreshadowing here so you can kind of pay attention to it as we're going through. the homework for Friday is going to be to modify our insertion sort here to, instead of work on a list of numbers, it'll work on a list of players, and it will sort them by those players' ages. Okay, so same logic, you just have to, it's gonna force you to solidify that idea of how do objects work and how do I get the individual elements of an object. All right, so for right now, let's go ahead and let's practice with our objects a little bit more. So I'm gonna go ahead and create a list of 100 players where they'll have first name 0, last name 0. We'll have an age between 15 and 75, and then we'll randomize the jersey number as well. I know we wrote this last time, but well, it doesn't take very long to write, so we'll go ahead and do that. So we'll create a list of players. Start that off as an empty collection, nothing's in there. And then I want to create 100 players for I in range 0 to 100. So we'll do something 100 times. And what am I doing each time? I'm going to add a new player to my list. So list of players dot append. And I need to call upon my player constructor, which requires me to give it a first name, a last name, an age, and a jersey number. So let me actually do those in separate variables here for a minute. So we're going to say fname is equal to fname concatenated with the string version of I. So we'll practice. I'll throw a couple different versions of this stuff in here just so we can see the differences. So first name is going to be fname followed by the string version of I. So I is 0. So the first time through, this will be fname 0, fname 1, fname 2, fname 3, so on and so forth. Now we'll do lname just a little differently. We'll do this as a f string. So this guy will be lname followed by I. So these two lines accomplish the same things, right? So this guy takes a string and glues onto it through concatenation the string version of a number. This guy right here takes advantage of an f string and says, okay, I'm going to have a string that's going to be lname and then a placeholder for my value I. So this will create lname 0, lname 1, lname 2. So these two guys perform the same operations. You can choose which of these two you like better. If I were to give you some knowledge, I think we've talked about this before with Python. It's like the thing you love and the thing you hate about Python is Python gives you a whole lot of power tools that allow you to accomplish some things very quickly in Python that other languages don't have. So Python is part of the core language, almost gives you too much what I refer to as syntactic sugar, ways of like doing things very shorthand, reversing lists and stuff like that. And it's great if you're just a Python programmer and you do Python all day, every day, and you can take advantage of those little kind of shorthand tricks and stuff. But the problem with that is if you learn that way in Python, then it takes a little bit more time to transition to a different language that doesn't have all those specialty little quick tricks. So every programming language is going to have a facility for concatenating one string onto another string. If we were working in Java here, I actually wouldn't have to convert it to a string. Java allows me to concatenate a number onto a string, and it will treat this as the concatenation operator as long as one of these two guys is a string. Where in Python, partially because it's an interpreted language, the way that concatenation works is it requires both sides to be a string. So I have to convert that number into a string. But regardless, every single programming language will have a facility for concatenation that roughly works this way. You know, you're not going to have to make this giant jump in logic to go the other direction. Only some programming languages have facilities for this type of thing, or common facilities, actually, I guess I would say. So really, this isn't even a fancy type thing. This existed in the original, in old C. We had a printf function where we would have said LName %D for our decimal I. So this is from the late 60s syntax there, where %D is my placeholder for a decimal value. So %D is kind of like this guy. So this isn't really a newfangled thing, just you don't necessarily have in every single language a way of doing formatted strings like this, or a very common way of doing formatted strings. Java has it. You can do formatted strings in Java, but it's not real commonly used. So you have to go and look up the notation for it in the documentation, and then you might use it all the time after that. But you know, punchline is if you wanted to just learn one way of doing it, and you just always concatenate this way, even though sometimes it's a little bit inconvenient because you have to string too many plus signs together, that would be a skill that would translate into every single language without any extra learning. Okay, but I'll give you both examples here. You can choose your poison. So this will be fname 0, fname 1, fname 2. This will be lname 0, lname 1, lname 2. Then we want to get a age. I said age is going to be between 15 and what, 75, something like that. So we'll say age is random.randint 15 to 75. And I think we saw that this does include the 75. So that's something else you want to kind of keep in mind when you use some tools from different programming languages, is whenever you have something that goes between a range, you want to kind of figure out, well, does it include the 2 endpoints or does it not include the 2 endpoints? Is this 15 to 75 including 15 and 75, or is this actually 16 to 74? In this case, this is 15 to 75, where in this case up here with range, it's 1 to this value minus 1. So they operate a little bit differently. So you just have to ask yourself, how does this tool work? What range of values am I going through? If I need a number between 15 and 75, do I do it this way or do I do it this way to get me including the 75? In this case, I think we saw a couple times ago that randint gives us this range inclusive. So this will give us numbers between 15 and 75 for age. And then for jersey number, we'll say random.randint. And we'll do a jersey number between 0 and 99, let's say. So up to 2 digits. All right, so in this particular time through the loop, we're going to remember 4 different things. The first name, the last name, the age, and the jersey number. Those happen to be the 4 things that are needed to build a player. We'll go ahead and build our player then. So we're going to append to our list of players a brand new player made up of my first name, my L name, my age, and my jersey number. All right, so this guy will boil down to the new player. If it makes you feel better, you can say a new player is equal to this guy stored in a variable, and then append to our list of players a new player. So if you like just explicitly putting things in variables and then passing just that simple variable to our append statement, that's fine. Otherwise, you can string it together. We could have done all of this in this one line right here. It just would have been a fairly, complicated line. All right, so this will go ahead and give us our list of players. Now, if I print list of players here, what's this guy going to print? What am I going to get a collection of printed to the screen?
Memory addresses?
Yep, a bunch of memory addresses, because objects, just like lists, are passed by address. So we're, this variable here, a new player, points to a place in memory where this player object exists with all of his stuff. All right, so when we append that to our list, this is a list of memory addresses which each point to a player. So there's my, list of players. Oh, my indentation is off. Wonder how that happened. Oh, so this is like shorthand. It says, here's a big list. We squeezed it into, so I guess I can click it for details and it'll expand it out. Did it do that the other day? I thought it gave me the whole list, but whatever. This is a list of memory addresses. That wouldn't be overly helpful anyways. All right, but now what I can do is I can tell those players to display themselves. If you remember from last time, we taught players how to display themselves in some sort of pretty print way. So now what I'll do is, rather than printing my list of players directly like this, I'll say for a player in list of players, a player dot display. So for each a player that lives in this list, so each time through, a player will be the next element in list of players. We'll tell that player to display itself. So there's all my players, F name 99, L name 99, age 16, jersey number 93, so on and so forth. Now, just for some additional, yeah, see, like the whole indentation level is off here. Let me try to do something. All right. I must have just been off from one time and then maybe hit a space bar or something. Who knows? So just to show you a comparison, because I think there's still some folks that are uncomfortable with these different types of loops. This is what I would call a for each loop that goes through for each element in list of players, set this variable equal to each of those elements each time through. So the first time through, a player will be this guy at bucket 0. Next time through, a player will be this guy at bucket 1, so on and so forth. If you want the equivalent of that for I in range 0 to length of list of players, a player is equal to list of players at bucket I, a player dot display. Those two things do the same thing. The difference here is this guy does not give me access to the index. This is similar to what we talked about at the beginning of today with our insertion sort. This guy does give me access to the index. I tells me where in list of players I currently am. I can then use that index I to get a specific player from that list. And I stored it in a variable called a player just to match exactly what's going on up here. And then I'll ask that player to display itself. So there's the same code twice. So these two guys will give me the same display here, but I don't have a variable called I. Well, I actually do from up here because it's in the same scope, but you know, this variable I is not found inside of this scope. So I don't have access to that I in a meaningful way. Whereas down here, I is part of this for loop. And because it's part of this for loop, I can use it to index in my list. Or I could just print out the value of I. And it'll tell me where I am in that list. So there was I, bucket 99, bucket 98, so on and so forth. Okay, so two different approaches to loops. If you need access to the index as well as the values, you would use something like this so you can keep track of where I am in the list and then use that value to get, or use that index to get a value from the list. If you only need the values, you don't really care where you are in the list, you could use a for each loop like this that just says, look, I just want this variable to be equal to each of the elements in this list. I'm going to do something with them. I don't care where they are in the list. I'm not doing any swapping or anything like that. All right, that makes sense? So this guy should implement our insertion sort for sorting players based on their age. So both of these loops print the unsorted. Actually, here, we'll just do it in the middle. Print the unsorted list of players. Then we'll call insertion sort. Insertion sort player ages. It's not legal right now since I don't have any values in there. Here, I'll just say print write code here. Print the sorted list of players with youngest players first. All right, so now we're combining what we did this from this last class with our objects, and we're going to write a second version of insertion sort that does swaps based on the players' ages. Okay, so same exact algorithm. I'm going to give you the algorithm we wrote today as the starting point. You'll just need to modify this to operate on players' ages rather than just a flat number. All right, questions, comments, concerns, bribes? Okay, I will see everybody on Friday. I'll go ahead and put this code up on Slack. And I'll hang out for a few minutes if anybody has any questions.
So there's no class on Wednesday?
Oh, who, what?
There's no class on Wednesday?
Oh, there is class on Wednesday. I thought today was Wednesday. That's how bad it is. Yes, there's class on Wednesday. I'll see you on Wednesday. Didn't I say earlier in the class that I thought today was, I think I was off 2 days to begin with. That's pretty bad. I need to go outside more often. Yes, we have class.